Hi, I'm Mike Seaman with Eta One Power. In this video, we'll introduce Eta Designer, a new tool from Eta One Power to quickly design, simulate, and optimize your power converters. Eta Designer is a standalone software package for Macs and PCs. I'll go ahead and launch the program. Eta Designer has a fully flexible schematic editor, which lets you draw any power circuit you'd like with these common components here. In the Place menu, we have a large number of additional components that can help you build your power converter, controller, or other circuit. Eta Designer supports hierarchy to make subcircuits you can reuse in all your designs. Eta Designer is all about speed. Instead of drawing your own converter, we can start with a template from a number of common topologies. We'll start by choosing New Converter Wizard from the File menu. In this example, we'll use an input voltage from 8 volts, a typical value of 12 volts, and a maximum of 24 volts. We'll set a fixed output voltage of 5 volts and an output current of up to 10 amps. We can require an isolated topology if necessary. Next, we're given a list of topologies that satisfy our requirements. We'll choose a simple synchronous buck converter. The next step is to specify the switching frequency. We'll choose 500 kHz. Finally, we can finish the wizard. Here's our new closed-loop buck converter. It's a fully editable schematic, so you can customize the circuit to your desires. Next, let's run a transient simulation to view the performance of our initial converter. The transient simulation finishes nearly instantly. Eta Designer is based on a proprietary, ultra-fast simulation engine, which allows you to access all these design and simulation tools without having to wait. The transient simulation is stable right out of the box, but clearly some improvement can be made to speed up the response. Now, let's examine the controller module to see how to improve the transient response. We can have any number of analog sense inputs. Here we have a single voltage input for our voltage mode controller. We can have any number of PWM gating outputs. Then we have a list of analog references or ramps, such as our PWM ramp, and a filter V-loop to represent our error amplifier. Finally, we have a graphical representation of our gating waveforms, one for each output. We can drag the output edges back and forth to arrange them as desired, then double-click on each edge to set its constraints. For example, this dead time is set as a 20 nanosecond delay after the falling edge of the low side PWM. Similarly, this edge is also set as a 20 nanosecond delay from the falling edge of the high side PWM. This edge is set as a period constraint from the previous falling edge, set to 2 microseconds based on our 500 kHz switching frequency. Finally, we'll look at the edge's constraints. The high side PWM is turned off when the output of the error amplifier, called V-loop here, falls below the PWM ramp, just like a traditional voltage mode PWM controller. Now, we'll look at how the error amplifier is defined. The filter interface provides the option of a proportional, PI, or PID filter. The typical characteristics are shown here. You can specify the gain and pull in zero frequencies. Once you have these worked out and stabilized, you can convert them to feedback network resistor and capacitor values to work with an analog controller. If you're building a digital controller, like using a microcontroller, you can get the difference equation coefficients as well. You can also look at the Bode plot of the loop gain of the system. In real time, you can adjust the gain to see how the stability of the system changes. You can also adjust the pole and zero frequencies to improve the response of the system in real time. However, we'd like to adjust the response of the controller while looking at a step response. Let's start by defining variables for some of these values. Eta Designer allows you to parameterize almost every value in the project to help you optimize your design. Let's take a look how that is done. We enter the variable gain for DC gain, and then FZ for a 0. We'll set this pole to 10 times FZ as well. Now we'll click OK. We see that we need to define the variables before going further. We'll choose Edit Design Variables from the Simulate menu, and then add 2 new variables. The first one, called gain, is our DC gain with a typical value of 30K. We'll set a logarithmic range from 10K to 1 meg. Now we'll specify Fz, the zero frequency, and set that to 30K as well. We'll have it range logarithmically from 10K to 100K. We can start by looking at the transient response, but we really want to look at the step response. We'll now configure the step response to apply a step to the design variable iout. Being able to apply a step to a design variable means you can examine the sensitivity of the design to many types of disturbances. We'll set the step to 5 amps and the step duration to 100 microseconds. We'll now run the step simulation, and then we need to select the signals to display. We'll select the output voltage and the inductor current. Here's our step response. As a low current goes up, the output voltage falls and then has some ringing. Let's see how we can improve this transient response. We'll show the variable sweep control, and we see how the response changes as we change the input voltage in real time. We can now select our gain variable and see how the response changes as we increase the gain. The response becomes faster, but becomes unstable as we increase the gain too much. Now let's adjust the zero frequency to smooth the response. Okay, now this looks like a good, fast response. Now we can close the window. I'm now prompted whether I want to save the design variables. Since we've improved the control parameters, we'll click Yes. Now we'd like to take a look at the converter efficiency using the tools in the Simulate menu. But first, we need to define our transistor models. By default, the model is ideal, so we can specify on-state resistance, saturation current, and so forth. However, we need to set these devices to use real component models. We'll choose Convert to Library Component from the Library menu. We can now select a model. We have a list of available models with this voltage range. We can expand the voltage range to include 60-volt transistors. Eta Designer substitutes each of these models into the circuit to obtain the component loss and converter efficiency. It also looks up the component's pricing and availability. This way you can examine these values and pick the best device quickly based on your own criteria. We'll choose a device here that gives us the best efficiency. We'll click OK to select this component and then pick a high-side device as well. The next step is to choose an inductor. Eta Designer has libraries from several component vendors, which allow you to select devices within their catalog. We can convert the inductor to a model component, and now choose the part which yields the highest efficiency. We can also choose models for the other components, like the output capacitor. We can now examine the efficiency of the converter over output current. As we've already chosen devices which maximize the converter efficiency, the efficiency is already quite good. However, it's always useful to examine where your losses come from. We can run an efficiency breakdown to understand our losses by component and type. We see that the losses are well distributed among our components. We can also view losses by type. Here we see that the conduction loss, gate drive loss, and capacitive switching loss are dominant at this operating condition. We can see how the losses vary as we change the input voltage, as well as the load current. If one or two loss mechanisms are dominant, you can see where your system bottleneck is and make a device or design change to improve your system efficiency. Now, we can examine the other optimization tools in Eta Designer. In our efficiency simulation, we can enable a secondary sweep to vary a second design variable or to examine efficiency as we change a component model. Here we can pick a few components to compare different MOSFET models for the low-side transistor. Here's a converter efficiency using the selected models over the load current range. Some devices do better at low current, while others do better at high current. This red part looks great over all the load conditions. Let's explore the other simulations. We've already explored the control and step response simulations. There's an FFT simulation to explore the harmonic content of any signal in the circuit, useful for conducted EMI analysis. In the Optimize menu, we can look at the Pareto front analysis to simultaneously optimize several design decisions. There's also a Monte Carlo simulation to let you understand how component variation can affect your circuit's efficiency and stability. Finally, there's a scripting capability to automate device selection and converter optimization and to create custom analyses. As you've seen, Eta Designer has many tools to allow you to quickly design, analyze, and optimize your power converter projects. These features allow you, as a power converter engineer, to reduce risk in your designs, eliminate unwanted prototype iterations, reduce engineering costs, and speed up time to market. I hope you've enjoyed this video and have learned how to use Eta Designer to quickly and efficiently design and optimize your power converters. Please check us out at etadesigner.com to download a trial version and to view more instructional videos like this one. Thanks.